called Weave Scope, and this is about visualizing your microservices applications. I stopped working this about 6 months ago, but during the time we built this open source project. It's got a very pretty UI. The UI team in Berlin did an absolutely fantastic job. But mostly this year, we built a hosted version of this called Weave Cloud, which you can go and use if you like. And running a service meant we had to monitor it. So, through recommendations of my friends, I was told to check out Prometheus, and we instrumented Scope and the service with Prometheus, and we absolutely loved it. And we're like, hey, about 6 months ago, we were like, hey, we should include Prometheus and a Prometheus service in Weave Cloud because it's so useful. And so we set down the path of how we're going to build a scalable version of Prometheus that we can use to provide a Prometheus as a service. So that's how we got here. In the process, we've moved everything onto Kubernetes. So that's kind of a bit more synergy with this conference, I guess. And we did a series of 4 blog posts last month, I think, maybe the month before, about our experience of using Prometheus and Kubernetes together. So, they're on our blog. You can check them out. They're kind of interesting. I mean, the best one is this deploying one. This is kind of the thing not often talked about of how to actually set up and deploy a production, grade Prometheus on your Kubernetes cluster and what the different trade-offs you have. The monitoring the applications, everyone's written about that. So there's not much point in reading that one, to be honest. Anyway, I've plugged the blog. Let's just dive straight into the design of the system. And like every good engineer, we sat down and we collected some requirements, and we had Fabian and Bjorn over to the office. Fabian and Bjorn are the other Prometheus core developers, or some of the other ones. We had them over to the Weaveworks office, and we talked to them about this idea, and they were really encouraging, and they basically completely changed the design in like 1 half-an-hour meeting, which was fantastic. We started off, we love Prometheus. We love the query language. It's really concise, and it's really powerful, so we're like, we definitely want to be completely compatible with Prometheus. And to the extent where, if you go and look at the code base, we just reuse wholesale massive swathes of Prometheus code. We just vendor in the Prometheus project into our binary and just call into it. It's fantastic. We also, we're a very small engineering team at Weaveworks. We've got about 20 of us. And on the Weave Cloud project and on this project, there's like 5. So on this project, it's actually just me and 2 other people, and Weave Cloud and the hosted version of Scope, maybe 2 or 3 more people. So this had to be super easy to operate, and we had to build this thing so that it just had to be easy. It had to scale. It had to not have any single points of failure. It had to generally be easy to upgrade because we do continuous deployment and we're redeploying this system 8-10 times a day. We're pretty ambitious. We want thousands of users. I think we've got like 10 right now. But we want thousands. And we want to make it cheap to run because we want to sell it. We're a company. We believe in open source. Everything we do is open source. But we're going to run out of money sooner or later, and by then we'll hopefully have a bit of revenue to pay for these things. So we do want to sell this eventually as a service and take all the kind of operational load off of the users. Yeah, and we wanted to reuse as much as Prometheus as possible. Prometheus is one of the best pieces of software I've ever worked with. It's one of the nicest code bases I've ever worked with, and it's just really high quality. And so we wanted to, reuse that. So yeah, don't worry, this is all open source. I know people get kind of a bit worried about this last bit here, but I like to be really, really honest about these things. We are a company, we are trying to make money, so we do want to sell this, but it is all open source, and we're 100% committed to this. We've done all of the development of this in the open. So I published, with Julius, and I published a design doc under the old name on the Prometheus developers mailing list. Oh yeah, sorry you can't, well, it's not that interesting, but just got some dates on it. Yeah, we started the design doc in June. We put the first jobs up about a month later into our cluster, and it kind of worked. And then a month after that, I presented this at PromCon in Berlin, where it was just about working by then. And since then, we spent a lot of time making it a lot more robust, and today I'm talking about it at KubeCon. So yeah, if you want to check out the design doc, it's kind of interesting. Doing the whole open design thing where you get feedback from people in the community who basically know more than I do about this stuff was a really interesting experience to me, and I'd massively encourage it. The GitHub repo that we did the development in was open from day 0. This wasn't we're going to go away and write thousands of lines of code and then magically open source it and make a big PR thing out of it. We started with an empty repo, and it was always open source. In fact, I think it started as a branch, as a fork of the Prometheus repo. So it It wasn't an empty repo. Anyway, so next, what does the system look like? Well, we've broadly divided the problem up into 3 different services. Microservices are all the rage, so we thought, hey, why not do that? And we've got this retrieval agent that you'll run in your cluster. This will scrape the jobs, do the service discovery that Prometheus is already good at, and will send all the samples in batches over to Weave Cloud. So in Weave Cloud, we've got a front end. This already existed. This is like the only bit of closed source code in the whole thing, right? And it's mainly closed source because it's embarrassing. But we'll fix that at some point. It was Nginx, now it's Go. It'll probably be something else in a few months' time. But now we really get into the Frankenstein bits. And we've split the job up into a distributor. And this is the thing that basically acts as the Frankenstein front end. Oh, it's not called Frankenstein, it's called Cortex. As the Cortex front end. And it decides where to route the request to, basically. And it deals with things like replication. And then we've got the ingesters. These things will collect samples, batch them up. And when they've got a big enough batch of samples, called a chunk, they'll get flushed to S3, where we store the chunks, and an inverted index in DynamoDB, so we can later find the chunks. So let's walk through that one more time, just to hammer this home. Your samples start in your jobs, exposed via the Prometheus/metrics endpoint. And the scraper, the retriever, will come along and scrape them into a little batch, not the same as a chunk, but a little batch. And then it will send them over via the front end to one of the distributors. Now, at this level, we're just using the queue proxy to do random load balancing. So we don't really have control over where they're going to hit. That's desirable, because that means these distributors are completely stateless. So if one of them misbehaves or we want to scale them up, it's super easy. It works really well. But then once they get to the distributor, we must start thinking about some of the Cortex-specific logic. So what we've done is we've used concepts from Cassandra Distributed Database. So we have a hash ring. I'll go to the whiteboard in a minute and draw this out. But basically, each sample belongs to a specific time series, and each time series belongs to a specific ingester. So we use this routing information that we maintain to break this batch of samples up into different samples that are sent to different ingesters. And then this process repeats itself, and eventually, I'm sorry, I've got an animation in, but I think it looks good. Eventually, you've got enough samples in an ingester to form a chunk, and the chunks will then get written to S3 and indexed in DynamoDB. It's really straightforward. Now, a few things to note. Queries are also handled by the distributor. Julius and I went round on maybe we should have a query service, but at the end of the day, the code just lives in the distributor. The ingesters have to have an in-memory inverted index as well, so that you can find the queries. And I'll give you some examples in a minute of how that works. What else should I mention here? Why have we got this separation between retriever and distributor? Is because mainly, your code's going to hopefully live behind a firewall. It's going to be really hard for us in our data center to scrape your jobs. So another thing to note, the retriever is actually just an open source Prometheus. And one of the questions before the talk I had was, has any of the changes we've made in the code we've developed gone upstream? And yeah, in the retriever, there's a generic write API, or SPI, I guess, that you can implement, that Cortex is one of the implementations of. So basically, you can tell Prometheus to send your samples somewhere else. So this here is just an open source upstream Prometheus. Works with 1.2 and 1.3. And why are we doing this interesting batching model here? This is because S3 doesn't really deal very well with 16-byte objects. You couldn't write every sample to S3. You'd just destroy it. Similarly, Dynamo does deal very well with small objects, but it's incredibly expensive. So by batching up the samples into chunks, you manage to basically minimize the cost of the cloud services we use. To give you an example, I think we're using the double delta encoding right now, and we get about 300 samples per chunk. There's about 10 writes per chunk into DynamoDB. I'll get into more detail later, but DynamoDB stores an inverted index, so every label value pair has to be written into DynamoDB. And so on average, we found it's between 8 and 10 users who are using our system have that many label value pairs on each metric. So if you multiply that out, for every sample that comes in the front end, we write about 0.03 of a write to DynamoDB, which makes this system cost effective. If we didn't have this system, basically we'd be charging users eventually one day, thousands and thousands of dollars to run this, and yeah, they're not going to do that. Anyway, let's go through each system a bit more. How do you set this up? So, as I said, Retriever is a vanilla open source Prometheus. Go and download it from Docker Hub or the Prometheus website. All the service discovery scraping that you know and love about Prometheus, if people don't know what I'm talking about, then hopefully someone else will cover that later. But I can go into it in detail if you like. All you have to do is add this to your configuration. Previously, these were command line flags, but now it's in the config, and you can put some credentials in there, and you put an API endpoint. The whole idea here is that you can also, if you don't want to use Cortex, if you don't want to use Weaveworks, or you want to host it yourself, you put your own URL in there. Or if you want it to send it to a Kafka or something else, then you build a little proxy for doing that, and you put that in there. This is the generic, completely non-Cortex specific bit of the project. And there's some PRs down here which did all of this. One of the interesting, so there was another project announced at PromCon a few months ago, basically doing a very similar thing by DigitalOcean, called Vulkan. And one of the big, people ask me what is the difference between Cortex and Vulkan. One of the big differences is they've considered the scalability of the retrievers. So they have a method for sharding their retrievers out, so they can run tens of retrievers, hitting millions of targets. We didn't. We just didn't think of that. The retriever is not really a bottleneck in this system. It is a single point of failure in the current setup, but the idea would be you just run two. So that's not actually, we do deduping on the server side, so that's not actually a big deal. But yeah, that's one of the differences between Vulkan and Cortex. So back to here, we've covered the retrievers. Let's move on to the distributors. This is kind of maybe the most hardcore distributed system bits of this. Have you guys seen Cassandra's virtual node implementation? Yeah, okay, one guy's nodding his head, great. It's based on Dynamo, the original Dynamo paper from Amazon, and it considers this token ring. You consider this to be like 0 to 2 to the 64, and then you pick, each ingester that comes along will pick a bunch of random points in this ring. Just sit there, pick a whole bunch of random numbers, insert them into the ring, and say, I now own everything from this random number to the next random number. So the nice property of this system is it gives you a completely even layout of distribution. Like the more random tokens you inject, the more even the distribution between ingesters become. The downside of this system is it's just complicated. You have to do, as Julius and I found out in the past few months as we've been implementing this particular feature, if you want to do replication, you basically start with a hash in our sense, it's a time series, it's a fingerprint. You start with the hash, you look for the key closest to the hash, and then you count, say we're doing replication of 3, you'd count 3 steps around the ring. And that would be your replica set. But you've inserted multiple tokens for each ingester. So you need to count 3 times around the ring, but not double count and not treat the same ingester as 2 replicas for the same sample. So now we're going to dedupe it and do the next 3 distinct ingesters. But what happens if an ingester is leaving? Because we've shut it down because we're doing a rolling upgrade. Okay, so we now have a state associated with each ingester. We count around the ring, and if we encounter a leaving ingester, then what we do is we increase the number of replicas we want. So we run with 3, but if we hit a leaving one, we ask for 4. And then we don't send the sample to the leaving one. Otherwise, it will just never get a chance to fully flush out to S3. And then similarly, you have a mirror of this if you're doing reads. If you're doing reads, you need to increase by 1 again, and then do your read from an extra 1. Otherwise, you might potentially miss data. So just one last point on the distributor. When you've finally got your replica set, your 3 or 4 or maybe even 5 nodes that form your replica set, you need to do a write to them. And it's really inefficient to write to every single one of them. And of course, we want to tolerate failures. So if we try and write to every single one of them, wait for them all, and one of them fails, So what we actually do is we write, this is currently what I'm implementing, so right now we just write to all of them. If one of them fails, it doesn't really matter, we just make sure we've written to at least n over 2 plus 1, so at least a quorum of them. And the whole idea of writing to a quorum of them is that you're guaranteed that a subsequent read that might hit a different quorum will at least have a single overlapping ingester. So that's where the +1 comes in. So yeah, it's kind of cool. Like this, in a previous life, I started a company called Akunu, which did the virtual node implementation in Cassandra. And if you go here, there's a presentation, funnily enough, by me, like 6 years ago, discussing exactly the same topic in the idea of big data and NoSQL. So it's there's no new ideas in computer science, right? Anyway, so Distributor also handles queries. In Cassandra and in other DHTs, this ring will be gossiped around the cluster using the gossip algorithm and CRDTs. We didn't bother doing that. We just stuck it in console. It made a couple of edge cases slightly easier to reason about. One of the things I was talking about doing maybe over December when it's a little bit more quiet is using Weave's mesh, which is our gossip library, to also make this gossiped. And that should make it much easier for people who want to run this themselves to get started. Let me see. So Dynamo-style replication. We've talked about console. Yeah. So that's the distributor. In our system, we're actually only running 3 of these. They're not particularly resource intensive. All they're doing is figuring out where to forward the data to. They do run queries, and so the more you have, the faster your queries. But we're in the early days. There's not a huge number of users on the system yet, so 3 is enough. The ingesters, on the other hand, we're running 6 now, I think, because these are the ones doing the real heavy lifting, and the chunking scheme is really kind of the key. Sorry about the whiteboard. I didn't think I'd put anything in the left. Anyway, so the ingester started off life as a heavily modified version of Prometheus, and we would push data to it, and I'm not going to get into a push versus pull debate here, but we were pushing data to it. It would then effectively use the memory series storage code from within Prometheus to chunk this up. It used exactly the same chunking scheme as Prometheus. This was developed by Bjorn, and it's just absolutely fantastic. It's one of the most interesting pieces of code I've ever had to stare at for hours on end. And it's heavily inspired. Bjorn gives a fantastic talk about how it's really inspired by Facebook's Gorilla paper. It's Facebook, isn't it? Yeah, I think so. So go and read the Gorilla paper. Go and read the source code. It's really well commented. And one of the reasons we use the same chunk format as Prometheus is it's incredibly efficient, the chunk format in Prometheus. So we take these samples, we batch them up into a 1 kilobyte chunk, and the chunk format does all sorts of in-memory compression on them. So with the latest var-bit encoding, there's 3 different encodings for the chunk, but with the latest one, I think, if I remember correctly, it's 1.3 bytes per sample. And a sample is 128 bits, so is 16 bytes. So that's like 12, 13x compression in memory with no performance overhead, basically. It's absolutely fantastic. And again, this makes the system cost-effective to run. So yeah, the ingester keeps everything in memory for an hour. We limit the chunk sizes to 1 kilobyte or 1 hour, whatever we hit first. And this is mainly, in case we have an ingester failure, it limits the amount of replay and the amount of recovery we have to do. Oh yeah, in the inverted index. So this was actually inspired by Fabian. The indexing scheme in the Prometheus upstream is very different to the way we do it, basically. We store an in-memory 1-hour inverted index. An inverted index is the same thing that Elasticsearch or Google will use, right? It's where you basically take the corpus of text and you insert, for every word in that corpus, you insert an entry into the index. And then if you want to do queries like saying, please give me every document that has the word X and Y in it, then you just do a query for X, a query for Y, and a set intersection on the results. So we do that. We store this in memory at this stage. This allows us to have pretty fast queries, actually. For querying stuff in the last hour, it's milliseconds, if the Wi-Fi works. We'll then talk about the index we use in DynamoDB is similar but different, and it's kind of important, the difference. So yeah, if one of these ingesters fail, you're going to lose up to an hour's worth of data. We have the replication to work around that. So right now, really, you'll only lose data if 3 replicas fail. But that's not really good enough for us either. So we're going to add, we haven't got around to doing it, but we're going to add a write-ahead log that will log out to disk. And if something fails, we'll have a manual step to recover that log so that you don't lose data. One of the big differences between Cortex and Prometheus is the concepts of durability and how long we can retain data for. So we really want to make it as durable and have the best retention as possible. So back to the diagram. We've talked about the distributors, the retriever, and final step is how do we use DynamoDB and S3. So this is maybe the trickiest thing to explain, and I really haven't come up with a good way of explaining it. S3 is easy. We just store the 1 kilobyte chunks as objects in S3. That's easy. There's just a bucket. But DynamoDB is a really weird database. Who here has used DynamoDB and programmed against it? Okay. You do count, Julius, because you wrote some of this, right? So, it looks a lot like Cassandra. So Cassandra has this concept of column families and rows, right? And the values inside the row don't have to be overlapping between different rows. So it's effectively just a set of nested dictionaries that are ordered. Okay? DynamoDB thought that was a little bit too complicated for people to get their head around, I think. So we're going to make it basically a list of items, documents effectively, and you can pick 2 keys in your document. One will be the hash key, and one will be the range key. Right? And the hash key is used for distributing data between nodes in DynamoDB. I mean, I've never seen the code for DynamoDB. I'm just inferring this is how it works from their documentation. And the range key is used for ordering items on an individual node within DynamoDB. And what this means for a user is you can't do range queries over hash keys, because that would have to consult every single node in your DynamoDB cluster. It would be terribly unavailable and really slow. And you can't do gets on range keys. So you basically have to specify a specific hash key and then a range of, a start and an end for a range key. So this is great, actually. We form our hash keys. They're not actually strings concatenated by colons. There's a library for doing really cool multi-dimensional array encoding into bytes in Go. If you look at the code, it's in there. I didn't write it. But it guarantees lexical ordering of the byte arrays. So this means we can do things. We would put the label name, the label value, and the chunk ID we just generate randomly, into the range key. And so we can say if you want to get all chunks for a given label and a given value, we just do a range key from label name, label value 0 to label name, label value, max int type thing. And that gives us all chunks in that range. And then similarly, we use this big bucket, small bucket scheme. So currently, I think we use hour as the key in the hash key. So we always know the hour we want to get the chunks for. And we use the metric name. This really does heavily affect how the system scales, but it's, again, a bit more esoteric. And we partition the first thing in all of our data stores is always the user ID. And this is really the only mention of multi-tenancy in the whole talk is you stick user ID in the primary key. So that was easy. I'll come back to explaining this a bit better later because it's tricky. This, the model here would work really, really well on Cassandra. We just didn't want to run our own Cassandra cluster. I've had too much experience doing that in the past. So, yeah. Okay, so that's the finished. That's all the stages in the system. There's a praying cat because I'm going to do a demo, and so far, every time I've tried to show it, it hasn't worked because of the Wi-Fi. I'm going to say at least. Right then. Everyone can see my screen. This is actually, we use Prometheus, obviously, to monitor Cortex. So I'll go through this dashboard in a minute. But let's go to cloud.weave.works. I'll show you the dev instance so we don't break prod. This is our product we're trying to sell. The Wi-Fi is awfully slow, but this shows you the topology of your application, which is kind of neat. So this is the front-end components of our application, and we can see what Cortex looks like on this. In Cortex, we've got the distributor that I talked about. You've got the ingester. You've got the console. Sorry, this is out of focus. I might make it a little bit bigger. Yeah. You've got the retrieval agents that I discussed. And then down here, you've got things like S3 and DynamoDB, DynamoDB, the internet, Memcache. Oh, we store the chunks in Memcache for speed as well. Anyway, I'm not here to show you that. I'm here to show you this. So this is the interface. This looks a lot like the open source Prometheus query interface, because it is. Again, we just vendor this in. This is actually something we've added in the past few days, so I don't really know much about how this little bit works. But it's just a little banner that helps you navigate the metrics inside Prometheus. So let's look at CPU usage. No, this one here. We let it load. Oh, 2.5 seconds to load that. That's pretty poor. But this is the standard Prometheus interface, and you've got the graphs as well. So this just shows you, you'll have to trust me that this isn't actually just hitting a real Prometheus. I guess what I could show you is, if I do cloud.weave.works in a different window and go to prod. So this one, if you look, is looking at dev, and this one will be looking at prod. And I put the same expression in. Go to graph and execute. And it doesn't work. Fantastic. Oh, no, there you go. So if you look between these two things, hopefully, I've demonstrated that this is really multi-tenanted because it's given you different data for the same query for different users. Haha. So yeah, so that's basically, it looks just like Prometheus, and that's by design because we think Prometheus is awesome. This little widget up here is really cool. David wrote this recently, but it basically splits the metric names on underscore and then builds a little tree out of them. And so you can say, oh, I'm really interested in Cortex metrics, and I'm really interested in the ingester, and I want to know stuff about chunks, and I want to know stuff about chunk age, and it's got it in seconds. Oh, and it's a histogram, and we don't help you with that. But let's just do a count and then do a rate of this. I'll make this full screen again. There you go. So that query is a bit quicker. Normal query latency on this thing has been about, in the order of maybe 500 milliseconds. We haven't done any optimization of the query path. Right now, we've just been focused on the write path. But yeah, that's the system, and it works. Oh, I was going to show you how to install it. We've got this cool installer that installs the node exporter and the Prometheus and points it at the cluster. But it's on our website. This is a dashboard that we use to monitor it. So I talked about how we've got chunks. The ingesters build these chunks. So up here, we've got the total number of chunks in the system. And you see, basically, because we flush every hour, and because we released this version at the same time as everything else, every hour you basically see this huge lump as we start flushing and duplicating all these chunks. And you see this down here is the length of the queue for the flushing. You see this go huge, and then we get lots of errors from DynamoDB. And then up here, we've got the number of chunks per series. So this should basically be always 1, because the minute a chunk gets closed because it's either old or full, we try and flush it. But again, every hour you see that spikes up and slowly dribbles down, and then, bobs along nicely. We've got some distributions here that I recently discovered are completely wrong, but basically tell you how full the chunks are when we flush them. So most chunks are completely full when we flush them, which is great. That's nice and efficient. How old they are, I was originally trying to design this system so that it'd be 1 hour old, but actually, for various reasons, because we're not using the most efficient encoding and because we're pushing much more data into the system than we thought we were, the chunks tend to be about 25 minutes old. And how many entries in them? They tend to have 300 entries in. OK, that's the presentation. That's the demo, really. Evaluation. Did this work? Well, I built this proper graph earlier today. This shows distributor latency. So when you send a chunk into the system, how long does it take to process and store that chunk? And the 99th percentile is 120 milliseconds. So I'm actually pretty happy with that. This is the 50th, which is 60 milliseconds. And the average, no, that must be the average. This is the 50th down here. The interesting thing here is this is only ever doing pretty much in-memory operations. So why does it take 120 milliseconds to do in-memory operations, right? And if you look at the individual ingesters, the latency for a chunk append, for a batch of samples append is actually, 6 or 7 milliseconds. So most of the time, I think, is being spent, because we're writing to all 3 ingesters, when really we only need to kind of write to 2, return, and let the third one kind of go along later. But also that calculation I was saying in the ring when you need to try and work out the replica set, I think is quite expensive. And I think we could probably improve that algorithmically so it wasn't so expensive. Queries, so to give you some context, this was on a system with about 1 million series in it. This was about 100,000 samples a second being added to the series. So a single Prometheus could do this just as well, to be brutally honest. But this was only running on 6 nodes or 5 nodes, so it's not a particularly large system. And yeah, about 100 milliseconds, 120 milliseconds at the 99th percentile. Queries is a different story right now. My next job is to optimize the hell out of this. But The peak of this is at 100 milliseconds, so that's not too bad, I guess. And down here, this is generally, I think, when people just weren't using it. So 100 milliseconds for a query is probably reasonable. The big problem actually is just the queries generate quite a lot of data. They have to fetch quite a lot of data, they have to process quite a lot of data, and the response contains quite a lot of data. So when this goes through the horrible auth thing the authenticating front end I was referring to earlier, this actually kind of gets delayed by a couple hundred milliseconds as we copy massive blobs of JSON around. So I'm hoping to optimize the hell out of that as well. We're seeing that across all of the service in Weave Cloud. Why not just run my own Prometheus? Well, we do, right? That's how we monitor Cortex. And you probably should as well. Prometheus is, as I said, one of the best pieces of software out there. Prometheus intentionally has a very different story around high availability to Cortex. So the story in Prometheus is run 2, and then you've got the most reliable system you ever will possibly want. And that's great. That works really well. And that's how Google operate, that's how we operate, and that's how most people should operate. There are some downsides to running your own Prometheus. If you do have a failure, you might get a few gaps in the graphs, although that shouldn't be too hard to fix. One of the other things, like, you might want to share the access to the Prometheus. We'll probably do some dashboarding that you might want to share in the future. So you need access control, you need authentication. Weave Cloud does all of that. That's kind of what we hope you'll pay for. Prometheus, is not trying to be everything to everyone, so rightfully isn't doing that. The other nice thing about this design that really contrasts it with Prometheus is we have virtually infinite retention of your data because we're not actually storing it. S3 and DynamoDB are storing it. And they are incredibly reliable systems. S3 seems to serve most internet sites on the web now, most websites on the internet now. So this is kind of maybe the biggest difference between Prometheus and Cortex is data retention. Prometheus is designed to run on a single machine, designed to be super reliable. It's designed not to depend on external services, and therefore is limited to how much data it can store on that machine. And typically you see people, we run with about 3-month data retention. I'm hoping once I start working on query optimization that I can start parallelizing the query execution, and start having a pool of query workers and doing tricks like that. And I'm hoping that our query performance will be able to exceed that of Prometheus's as well. But having said that, Prometheus query performance is pretty good, so that's a tough target. And we want to have a very different story about high availability. So not just having really good durability and retention, but should one of the availability zones in our Amazon data center go down, we want to have a different story and a better story around not having holes in your graphs during that process. There is a lot left to do. This is an open source project. There's only 2 or 3 of us working on it. So when I presented this slide in 2 months ago, none of it was crossed out. And since then, we've done a whole bunch of code cleanup. We've done a whole bunch of upstreaming. The replication between ingesters went in about a month ago. The life cycle of ingesters joining and leaving the cluster without the cluster going down and exploding, that went in about a week ago. Commit log and separate query services stuff we're going to work on next. And Jono, the other chap working on this, is currently implementing recording rules and alerting to kind of round everything off. So yeah. Oh yeah, and we probably should figure out a way to bill for it and implement rate limiting and stuff like that, because right now, if you sent me 1 million samples a second, you'd probably take the service down. Great, that's me, that's Tom. Any questions? If you want to try it out, I'll put the slides online so you can copy the code off that, but this is the way of kind of getting started. Go and sign up, put your token in here, and put this command into your Kubernetes cluster. Or check the code out and tell us if it works for you. So questions? So actually, in the past 4 days, the load on the system's gone up by about 10x. So I very much have been frantically scrabbling around behind our booth, scaling the system up to deal with that. So yeah, we wouldn't, the whole point of this system is each customer doesn't get their own Prometheus, because we want to have, we hope to have thousands of customers, and we don't want to manage thousands of Prometheuses. So instead of, sharding by customer, we're sharding, I didn't talk about this, did I? Oh, I completely missed it. We shard by customer ID and metric name, and we hash that into the ring. So the idea is this should be very horizontally scalable and multi-tenant. So if a customer does come along and try and DOS us, we should hopefully just scale the system up and survive.
Increase that likelihood of just trying to work with the open source community, make sure that Prometheus can handle that?
I mean, the challenge isn't going to be the performance of the chunking scheme or of anything like that. The performance is, our current bottleneck is actually how quickly we can flush stuff to S3 and how we use DynamoDB. Because DynamoDB is a statically provisioned system, so we provision it right now for, I think, a couple of thousand QPS. And if you start exceeding that, they throttle you. So we're currently exceeding, and that's why all the graphs were really colorful at the bottom of the screen, because we're currently exceeding that and we're being throttled. And I need to go and scale it up and think about ways of being slightly more efficient in our use of DynamoDB. I'll also, we'll just scale up and up. We've got funding from GV, so that's all being funneled to Amazon. Are we being, we're being recorded. Another question, chap at the back. Yes. So I said that again? Yeah, so each batch that comes in gets, we run a little algorithm which decides which sample belongs to which ingester, and then we split it up into multiple different batches and send them on. So there is a write amplification going on there. Oh yeah, so if one ingester is down, we actually only need, if we're writing to 3, which is what we currently do, we only need 2 to act the write. So if one ingester is down, that's fine. We can just, that doesn't really particularly matter. If 2 ingesters are down, then we've got a problem. But yeah, we only need 2 acknowledgements of the write from 2 different ingesters before. Both flush them. The data will be replicated multiple times in DynamoDB and in S3. Yes. So one of the things we want to do, because S3 itself is replicated behind the scenes, we want to have a background process which is going along and coalescing these chunks and maybe forming slightly bigger chunks to give you better performance for larger queries as well. We haven't got round to that, and it's not particularly important right now. Yes, 11.9's durability is a lot better than Cortex's availability. So it's not a limiting factor right now. I mean, our idea will be eventually when we're properly selling this commercially, we'll run it in 2 different locations, and we'll have a proper HA and so on. But right now, it's still pretty reliable. It's if you consider a single Prometheus node is as reliable as the machine it's on, I think we will eventually, once we work on it a lot more, get to better reliability than Prometheus, but at the expense of much more complexity. So it's going to take a lot of work to get there. Thank you. Any more questions? I think you had some questions, didn't you, earlier?
I think you addressed them.
Oh, okay. Sorry. Go on, you again.
Because you are a Amazon customer, you decided to go with Dynamo and S3 and consider other things like Kafka, or even using something that's not S3, like Cluster or file storage space?
Yes, we did. The main thing was we just didn't want to run too many big, complicated distributed systems. We believe, we're offering this as a service because we want to use systems that are offered as a service. We want somebody else's, the operation of the system to be someone else's problem, and we're happy to pay for it. On the other hand, the interfaces internally are designed such that you could swap this out for Cassandra. I mean, Cassandra is really the one that we've mainly kind of talked about, but there would be nothing to stop you using Bigtable or HDFS or maybe even React or something like that. The only interesting kind of side effect here is the chunk size is quite small. So 1 kilobyte is small even for something like S3. And it kind of fits, it kind of slips between the small value databases like Cassandra, which are very good at storing values of a few bytes in size, and the large value stores like S3, because that's just an easy problem. And there's kind of a gap around the 1 kilobyte mark of what do you do with 1 kilobyte? So a little bit too big to put in Cassandra. You probably just put them in Cassandra, but they're a bit too big. You'd have to tune your compaction settings. And they're a little bit small for something like Gluster or HDFS or so on. So that's kind of an interesting problem. I think, hopefully the coalescing system that I was referring to, when we get around to writing that, will allow us to build much larger chunks and do some deduping, and that will maybe make it more applicable for something like HDFS or Gluster or something.
Have you seen any significant performance problems with using object storage just as S3?
You know what? 99% of our stuff hits our mem caches. Most people just query the last hour of data. So, the actual read QPS from S3 is excruciatingly low. Yeah, we also do that because it makes it more cost effective because we don't have to pay if we get a hit in mem cache. The write performance for S3 is not as nice as we like, and it has some weird characteristics. You can kind of tell what it's doing behind the scenes, and it's clearly like forming ranges of keys and splitting them off and giving them to other machines because you see really weird step changes in the latency of S3 as you're running the system. But once if you tweak the name you give your keys, so if you give your keys in S3 like nice random distributions, then it actually behaves quite nicely. I must be, oh no, I've got 5 minutes left. Okay, I thought I was running out of time. Any more questions? Okay, cool. Well, please try it out. And we, as Weaveworks, have offices in 3 places. So, we're hiring. We've got offices in San Francisco, Berlin, and I work in London. So, yeah, if you want a job working on Cortex, then come and work for us. Thank you very much.